So as our first example, let's look at a very simple way of using a block cipher for encryption. In particular, we'll see how to use a block cipher with a one-time key. So in this segment, we're just going to use the block cipher to encrypt using keys that are used one time. In other words, all the adversary gets to see is one ciphertext, and his goal is to break semantic security of that ciphertext. Now in the next segment, we're going to turn into more interesting applications of block ciphers, and we're going to see how to encrypt using keys that are used many times to encrypt many messages. So before we start, I want to mention that there is like a classic mistake in using a block cipher. Unfortunately, there are some products that actually work this way, and they are badly broken, so I want to make sure that none of you guys actually make this mistake. So this mode of operation is called an electronic codebook, and it works as follows. It's the first thing that comes to mind when you want to use a block cipher for encryption. What we do is we take our message, we break it into blocks, each block as big as the block cipher block. So in the case of AES, we would be breaking our message into 16-byte blocks. And then we encrypt each block separately. So this mode is often called electronic codebook. And unfortunately, it's terribly insecure because you realize if two blocks are equal, for example here, these two blocks happen to be equal, then necessarily the resulting ciphertexts are also going to be equal. So an attacker who looks at the ciphertext, even though he might not know what's actually written in these blocks, will know that these two blocks are equal. And as a result, he learns something about the plaintext that he shouldn't have learned. And if this isn't clear enough for you abstractly, the best way to explain this is using a picture. And so here's this guy here that has this really dark black hair. And when we encrypt this image, this bitmap image, using electronic codebook mode, you see that his hair that contains lots of ones basically always gets encrypted the same way, so that his silhouette actually is completely visible even in the encrypted data. Okay, so this is a nice example of how the electronic codebook mode can actually leak information about the plaintext that could tell something to the attacker. So the question is how to correctly use block ciphers to encrypt long messages. And so I just want to briefly remind you of the notion we're trying to achieve, which is basically semantic security using a one-time key. So the adversary outputs two messages, M0 and M1, and then he gets either the encryption of M0 or the encryption of M1. These are two different experiments. And then our goal is to say that the adversary can't distinguish between these two experiments. So he can't distinguish the encryption of M0 from the encryption of M1. And the reason we call this security for a one-time key is that the key is only used to encrypt a single message, and as a result, the adversary will ever only see one ciphertext encrypted using this key. Okay, so the first thing we want to show is that in fact the mode that we just looked at, electronic codebook, in fact is not semantically secure. And this is true as long as you're encrypting more than one block. So here's an example. Suppose we encrypt two blocks using a block cipher. Let me show you that in fact electronic codebook would not be secure. So here's what we would do. So we're the adversary. So we would output two messages, M0 and M1, where in one message the blocks are distinct, and in the other message the blocks are the same. The two blocks are equal to one another. Well, so what is the challenger going to do? The challenger is going to encrypt either M0 or M1. Either way, we're going to get two blocks back. So the ciphertext actually contains two blocks. The first block is going to be an encryption of the word hello, and the second block is going to be either an encryption of the word hello or the word world. And then if the two ciphertext blocks are the same, then the adversary knows that he received an encryption of the message hello, hello. And if they're different, he knows that he received an encryption of the message hello, world. Okay, so he just follows the simple strategy here. If you think about it for a second, you'll see what his advantage is. So what is the advantage? Well, this adversary, when he receives an encryption of the message M1, he will always output 0. And when he receives an encryption of the message M0, he will always output 1. And because of that, the advantage basically is 1, which means that the scheme is not secure, which again shows you the electronic codebook is not semantically secure and should never ever be used to encrypt messages that are more than one block long. So what should we do? Well, so here's a simple example. What we could do is we could use what's called deterministic counter mode. So in deterministic counter mode, basically we build a stream cipher out of the block cipher. So suppose we have a PRF, F. So again, you should think of AES when I say that. So AES is also a secure PRF. And what we'll do is basically we'll evaluate AES at the point 0, at the point 1, at the point 2, up to the point L. This will generate a pseudo-random pad, and we'll XOR that with all the message blocks and recover the ciphertext as a result. Okay, so really this is just a stream cipher that's built out of a PRF like AES and Triple DES, and it's a simple way to do encryption. I wanted to just very quickly show you the security theorem. In fact, we've already seen the security theorem when it applied to stream ciphers using pseudorandom generators, so I'm not going to repeat this again. I'll just remind you that essentially for every adversary A that's trying to attack deterministic counter mode, we prove that there's an adversary B that's trying to attack the PRF. And since this quantity is negligible because the PRF is secure, we obtain that this quantity is negligible, and therefore the adversary has negligible advantage in defeating deterministic counter mode. And the proof in pictures is a really simple proof, so I'll just show it to you one more time for completeness. So basically what we want to show is when the adversary is given the encryption of the message M0, here this is the encryption of the message M0, M0 XOR counter applied to the PRF, versus in giving the encryption of the message M1, we want to argue that these two distributions are computationally indistinguishable. So the way we do that is basically we say, well, the top distribution, if instead of a PRF, we use a truly random function, namely here f is a truly random function, then the adversary, because of the property of the PRF, the adversary cannot distinguish these two experiments, right? A PRF is indistinguishable from a truly random function. Therefore, when we replace the PRF on the left with a truly random function on the right, the adversary is going to behave the same. Basically, he can't distinguish these two distributions. But now, because f is a truly random function, the pad here is a truly one-time pad, and therefore no adversary can distinguish an encryption of M0 from an encryption of M1 under the one-time pad. So again, these two distributions are the same. In fact, here there's an actual equality. These two distributions literally are the same distribution. And similarly, again, when we go back from a truly random function here to a PRF, because the PRF is secure, the adversary can't distinguish these two bottom distributions, the left from the right. And so by following these three qualities, basically we've proven that the things we wanted to prove equal are actually computationally indistinguishable. Okay, so that's a very simple proof to show that deterministic counter mode is in fact secure, and it's basically the same proof as we had when we proved that a stream cipher gives us semantic security. Okay, so that completes this segment, and in the next segment we'll talk about modes that enable us to use a key to encrypt multiple messages.